My name is Joaquim. I'm a physical layer engineer working for SRS. And my hopes with this talk is that by the end of it, you will learn how to perform power calibration using our own G-Node-B, and also to get maybe some key aspects about how power calibration works and what is the main purpose of it. So without further ado, let's get going. Oops. Yeah. Okay, so first of all, I'm going to introduce like an outline to this presentation. First, we are going to do a brief introduction about power calibration. Then we are going to talk about what of the srsRAN project G-Node-B configuration parameters are relevant for power calibration. I will explain all of them, and then you know what we are going to try to optimize. Then this will lead us into a proposal for a power calibration procedure that is a step-by-step guide that you can use to optimize your system. And then in the next point, that would be point number 4, I'm going to justify this procedure. As you will see, there are some things that might be a bit counterintuitive about this. And so I thought it was important to provide some explanations, and so that you have a deeper understanding about the implications about changing some of these parameters. And to finish the presentation, I'm going to show you some experimental results that I gathered using USRPs. And these results are going to lead to a conclusion that is, you really need to have a proper RF front end for a USRP to achieve decent performance on an outdoor environment. Okay, let's start. So, first of all, why do we do power calibration? What do we try to achieve when we do this? So, the main objective is that we want to maximize the uplink and downlink channel capacity. This is important because this regulates how much information per unit of time we can put in an RF channel, as I'm sure you all know. So in order to do this, we need to take into account the constraints that we face when we want to do this. So I'm going to present the most important ones. First of all, we have in an RF environment noise in the channel. There are many noise sources. We are going to talk about some of them, the most important ones. But basically, it could be thermal noise, interference that could be caused by other networks, or it could even be caused by our own network if we have multiple cells. Then we are also going to talk about the dynamic range of a receiver. This is going to limit also, like it's going to constrain how we optimize the power calibration parameters. And finally, of course, as in every transmitter, we have a maximum transmission power that we can use. The limitation can come from different aspects. So it could be that we are exploiting all the power headroom that we have in our power amplifier. Or it could also be that due to legal regulations, we have to adhere to a maximum amount of transmission power. So another important topic that we are going to see in this presentation, and it is related to power calibration, is uplink power control. So I don't know, well, in case you know, great. In case you don't, what happens in a mobile communication system is that the UE needs to estimate the path loss that is going to face when it transmits the uplink signal, because the G-Node-B needs or asks the UE to use a specific amount of energy in order to receive a signal that is in the target power. So basically, the way that this works is that some of like the G-Node-B transmits some information to the UE by a broadcast channel, is a configuration, part of the cell configuration. It transmits what we call the P0 nominal parameters for PUSCH, which is the physical uplink shared channel, where the data for the users is carried, and PUCCH, which is an uplink control channel. So basically, the G-Node-B is telling the UE, hey, when you transmit, I want to receive the signal at this power level. And then the UE needs to figure out how to do that. In order to do this, the UE estimates the downlink path loss. At least, well, that's one of the ways of doing it. It's one of the most common. So the UE also knows from the G-Node-B the power of the downlink signal. it specifically knows the power of the synchronization signal that is broadcasted by the cell. And then it also knows the energy at which it received this signal. Having these 2 points of reference, the UE can compute an estimation for the path loss. Then, if we are in a TDD scenario, it is a logical assumption to say that the uplink path loss is going to be very similar to the downlink one. And then the UE can compensate for this path loss when it transmits the uplink signal. This is how an open loop power control system works. In 5G, we also have closed loop power control, but in this presentation, I'm not going to get into that. So to sum up, the UE estimates the path loss. The UE knows what the received power the G node B is asking for, and with this information, it decides a transmission power. It could also be that the transmission power that is required is too high for the UE to transmit. So of course, if this is the case, the UE cannot go above its maximum transmission power. So for example, in the case that a UE has a maximum transmission power of 23 dBm, of course, it's not going to transmit more than that. The G node B needs to know, well, it is useful to know how much power headroom is available in a specific UE. This is why the UE uses a metric called power headroom, PHR. So this metric is transmitted to the G node B, and then the G node B knows if the UE is close to reaching the target, the maximum transmission power, if it has already reached it, or if it has ample headroom to transmit more power. This metric works in the way that the maximum value is 0. So if the power headroom is 0, it means that we have reached the maximum transmission power. If it is positive, it could be positive, but if it is positive, it means that there is still headroom. So for example, if PHR is 10, this means that the UE is transmitting 10 dBs below the maximum transmission power. And it could also be negative. If it is negative, the UE is saying, look, I'm transmitting at the maximum transmission power, and I'm still, let's say, 10 dB short of reaching the P0 target that you asked me to accomplish. All right, now that we have I've introduced the relevant aspects to power calibration, let's now discuss how you configure all of this in srsRAN. So first of all, for downlink parameters, you have here in this slide first a description of them, and to the right you have a very concise configuration example with only the parameters that we discuss. So you know when you configure, when you edit your G node B configuration file, which parameters and where to find them you need to tweak in order to apply the power calibration procedure that we will talk about later. So first of all, for downlink, one of the most important ones, of course, is the transmission gain of the downlink signal. So there is an important point to be made that this parameter, which is the one that is under RU-SDR category, is of course only applicable to SDR devices. So in case you are not aware of this, with our G node B, we can target both SDR devices, such as USRPs, or split 7.2 RUs. The transmission gain will only apply to SDR devices, so it's no point configuring it if you are using it on a commercial OFH RU. But for this kind of RUs, we have a parameter that provides a similar level of configurability, which is the IQ scaling. So the IQ scaling, because we don't have direct control of the transmitter chain when we use an RU, is a digital gain scaling factor. But you can use that to apply a scaling factor to the signal that is reaching the RU. And so it has a similar effect as the transmission gain. Then, moving on. Next parameter is the SSB block power. This I have already talked about. Remember when we talked about power control in the uplink, I said that the UE knows the power of the synchronization signal that the G node B is transmitting all the time. Well, this is the parameter that the G node B is going to broadcast in one of the SIB messages to the UE. So you should set this parameter according to the transmission power that the G node B is operating under. The proper way of doing this is to get a measurement of this. So in order to calibrate this parameter, you would need to have a 5G signal analyzer, plug it at the output of your G0B or RU, measure the power of the secondary synchronization signal within the SSB, and put the value that you measure in the configuration. Now I will show you an example of this. And then just to finish, we also have an amplitude controller module inside our physical layer. This is not a main topic of discussion for this presentation, but I just wanted to put it here so that you know it exists. And the point of this is to provide similar functionality to what you would get in an RU, where you will have protection over the power amplifier. So in case you are using a USRP and you are targeting a power amplifier, you want probably to limit the maximum amount of signal magnitude reaching that power amplifier to protect it. You can use the amplitude controller. What it's going to do is that it allows you to clip the IQ samples that are reaching the USRP so that you make sure that they don't exceed a specific value. By default, by the way, this is disabled. You need to configure it in order for it to work. And in my opinion, it makes sense to use it only if you have an external power amplifier that you really want to have a guarantee that the power will never exceed a specific value. Okay, as I promised, so this is an example of a commercial grade spectrum analyzer with a 5G application, which of course some of you will recognize. So in here you see the parameters of a 5G downlink signal, and then on the image on the right, it's zoomed in the power parameters that you can get. So from all of this list, in this particular example, the value that you need to look for and use to configure the SSB block power is the srsRAN. And the reason why is because this is the power per resource element of the secondary synchronization signal, which is what the standard says that the SSB block power needs to be set to. So it's not enough to just get a power measure and say, oh, I get 20 dBm, okay, I put 20 dBm. It doesn't work exactly like this, and if you do this, probably the system is not going to work very well. If you have any further questions about this, we can discuss that. Okay, and now with respect to uplink parameters, we have the receive gain, which works analogically like the transmission gain. It's only for SDR devices again, because with a split 7.2 RU, we cannot control within the G0B the receive gain of the RU. And well, I didn't say it before, but both the transmission gain and the receive gain, they can be configured at runtime through the console. So if you want to do that, if you launch the G0B and you want to play with these parameters, which is very useful in some situations, you don't need to stop it and run it again in order to change these values. And the next two parameters, which are the PUSCH P0 and PUCCH P0, again, are related to power control. And these are the power targets that the G0B expects the UE to fulfill when it transmits uplink signals. And they are not exactly power targets. They are spectral density targets. And the difference here is important. It's, the reason why we do this is because, of course, it could be that in a G0B, in a specific cell, we have many UEs transmitting uplink in different allocations. And we don't care about the individual power of each UE. What we really care about is that the sum of all the signals doesn't saturate the receiver. For this reason, it makes more sense to configure a spectral density target so that each UE knows not the total amount of power it needs to transmit, but the spectral density that we care for at the receiver side when we have to decode all the signals coming from all the UEs. And of course, here you also have a very brief example about these parameters, how you find them, and so on. Now, before moving on, I want to discuss very briefly what happens when, instead of having a USRP or an SDR device, we have a split 7.2 RU. Because as you have seen, there are some parameters that you simply don't have available. This doesn't mean that you cannot do the same. You can. Many commercial RUs support tweaking the transmission power of the RU. It is just that it is not possible to do it from the G-Node B configuration, but you can still apply the same procedure that we will talk just by manually configuring this in the RU. And with respect to receive side of the commercial RUs, normally what happens is that they are calibrated to a specific receive saturation point. So it could be, I don't know, minus 65 dBm or whatever. Some of them also provide control of this. So you could play with some attenuators inside the RU to make it more or less sensitive. Again, I'm not going to get into that, but just so you know that it should be possible to do this. And in the case that you already have an RU and you are happy, you are satisfied with the power target that the RU tells you to use, for example, in case you have RU that says, oh, yes, I expect to have a maximum receive signal level of minus 60 dBm at my input ports. Then the only thing that you need to be concerned about with respect to uplink is setting your PUCCH and PUSCH P0 targets so that this level of power is achieved. Of course, the most important thing is that you don't go over it, because then you would have saturation, or that you are not significantly below that, because then you are not exploiting the channel in its full capacity, and the internal noise of the RU is going to limit the performance of your system. Okay, so now that we have talked about all the parameters, we have to discuss what metrics you can get out of the system in order to see what's going on and to achieve the proper calibration. So first of all, for PUSCH, well, I didn't say it, but what you see below is an example of our console metrics, which I'm sure most of you are already familiar with. Just so you know that these parameters, you can always find them here, so you don't need to go into the logs or do anything strange to get them. So the PUSCH srsRP is a power measure, and the idea is that this tells you how far you are from saturating the receiver, and also the expected level of SNR that you will get, the expected level of performance. So basically, it's always negative. The biggest value you can get is 0. This is in dB relative to full scale. So of course you know that if it reaches 0, it means that you are saturating. Then values close to 0 probably also imply saturation, because this is an average power metric, and the 5G signals, because it uses OFDM modulation, has a relatively high peak to average power ratio, which its abbreviation is PAPR, which means that you need to have some level of overhead to accommodate for this. So basically, in my experience, when srsRP is between minus 10 and minus 20 dB relative to full scale, it's probably a sweet spot for this metric. We also have the PUSCH SNR, which, in case it's not clear, it's this over here. So the column labeled PUSCH is actually the SNR. And of course, this gives you a direct metric about the channel capacity, so the quality of the signal that you are receiving. And then you also have the power headroom, which we discussed before. In this case, it is 27, which means that the UE is telling the G-Node B, hey, I'm transmitting to reach your P0 spectral density target, and I still have 27 dB of headroom left to increase my transmission power. So it looks not bad in this case. Okay, so just a summary. For downlink parameters, we have the transmission gain or IQ scaling, in case you have a commercial RU. We have the SSB block power, which is a parameter that we measure and set. And for uplink, we have the receive gain for SDRs. And then we have the P0 nominal targets for PUSCH and PUCCH. And then in terms of metrics, we have a power metric, which is the srsRP in the uplink, a channel capacity metric, which is the PUSCH SNR, and a power headroom metric coming from the UE. Now, what do we do with all of this information? So in this slide, you have what I propose to be a power calibration procedure. So first, I will explain each point a little bit, and then we will justify, because maybe some things are a bit, well, not strange, but not directly intuitive at first. So the first point is actually very intuitive. It means use all the available transmission gain you have until you reach whatever limitation you are facing, whether it is legal or just the headroom that you have for your power amplifier. So in case that the limitation is the power amplifier, what does this mean? Well, it means that you can keep increasing the transmission gain, but there will be a point where doing so will result in signal saturation in the downlink. And how do you, in case that this is the limitation you are facing, the proper way to find the limit is, again, to use a 5G signal analyzer that you can see a metric of error vector magnitude, or EVM, and also the out-of-band emissions, because as you know, like these are the two main drawbacks when you have saturation in a transmission chain. One thing is that it will degrade the signal, so the information that is being carried by the signal is affected, that is not going to be so easy to decode in the receiver. And the other problem is that you will transmit out of band. And then you could be going over the spectrum emissions mask that is a requirement for a specific band that you can transmit on. So again, this is something that needs to be measured, and yeah, that's it. In case you are just doing it in a situation where you are not transmitting, you're not broadcasting outdoors, and you don't really care so much about the out-of-band emissions, the only problem that you should look for is the EVM. So it's going to reach a point where increasing the gain is not going to result in better performance, because the signal is being degraded before it actually goes over the air. Okay, so once you determine and you set the maximum transmission gain that you can use, then you measure the SSB block power at that specific gain. So of course it doesn't make sense to do it a different way, no? But you could always extrapolate. So you could always say, oh, I measured the SSB block power at a transmission gain of 60. Now I reduced it to 55. So probably subtracting 5 from the SSB block power should be good enough, no? Okay, then the next point is actually the most difficult one to justify, and this is determining an optimum receive gain for your SDR device. This we are going to see in more detail. Then once you have done this, the way that you get the information out of the system is to attach a UE, run uplink traffic. I mean, the idea is to use all the entire band, and then observe the PUSC, the metrics, no? The SNR, the RSRP, and the power headroom. And once you have done this, with this information, now you can adjust the parameters. So one thing that you probably want to do is to adjust the P0 nominal. And the way I would recommend doing is adjusting the PUSCH P0, because that's the one that you have information of, because you have the PUSCH SNR, RSRP, etc. And then once this is done, you can probably set the PUCCH P0 to a value that is below the PUSCH P0. And the reason for this is that the PUCCH channel uses less spectral efficiency. So basically the data that is carried over this control channel has more redundancy, and it can deal with more degradation. So it's probably fine to, for example, use 10 dB below the PUSCH P0 for PUCCH P0. And actually, doing measurements of commercial cells with analytic software, we see that this is what they do as well. So once you have adjusted the P0 nominal parameters, in order to move between, as I said, minus 10 or minus 20 dB FS for the RSRP, at this point, you know that the power that is reaching the G node B is within like a specific window that it should not be causing issues. But we can still further optimize the system. So at this point, you can either see one of two things. You can see that even if the RSRP is between this window, minus 10 and minus 20 dBFS, you could see that the SNR of the PUSCH is low. And so what could be happening at this point is that even though the power reaching the G node B is within a specific window, there is significant contributions from noise or interference. In this case, a way that we can deal with this is to decrease the receive gain and increase the P0. I will explain why later. Another thing that could be happening is that the system is performing very well, but it has a very limited range. And you can see that if you pay attention to the power headroom that the UE reports. So what you will see is that if you have the UE very close to the radio, maybe the power headroom looks fine. But the moment you start moving away from the radio, the power headroom quickly decreases and it goes all the way to 0 and it even goes negative. If you see this happens, and if this is a problem for you for the tests that you're doing or for your deployment scenario, then you can do the opposite. You can increase the receive gain and decrease the P0. And this will mean that the UE needs to transmit less power in order to reach the specific P0 nominal target. After this explanation, you might have some questions. So, first of all, I say, increase the P0, so increase the power, the power spectral density target if the srsRP is low. And by low, I mean below -20. This -20, by the way, is just a value. Normally, we try to be between -10 and -15, but it's just to have like 10 dBs of range. So you could be asking, yes, I can do that, and this means that the UE transmits more power, so it will increase the srsRP, but why not increase the receive gain? Because this will also result in higher srsRP at the G node B, because these measurements are taken after the signal is converted into the digital domain. So if I increase the receive gain, the srsRP also increases. And this is a valid question. And then there is another question that is, hey, you're saying that if the SNR is low, decrease the receive gain. And this is, maybe you could be asking, wait, if the SNR is low, maybe I should increase the receive gain, no? Because then I have a healthier signal level and maybe things improve. It depends how you look at this. And now what I will try to do is to justify these statements. But in order to do that, first we need to talk about the main noise sources in a very simplified model of a receive chain. So first of all, in here you have like a very, as I said, very simplified schematic of a receive chain. It doesn't take into account the IQ, the modulation. It doesn't take into account the filters that you would probably have before the low noise amplifier. All of this is not present in this analysis. It's just so that we can see the noise sources and how controlling the receive gain affects them. So first of all, we would have internal noise. And this internal noise can come from the low noise amplifiers in the receive chain. It can come, and a part of it always comes from the analog to digital converter. So as you probably know, if you have an analog to digital converter, there is a quantization error. This quantization error, which is not noise actually, we can model as noise, which is why we say that it's a quantization noise, which is technically not true. But let's say, for the sake of the discussion, that it's actually a noise. Then, because of the location of these noise sources, what happens is that if I increase the receive gain, which I'm assuming that it's a control that is present in my low noise amplifier, the quantization noise is not affected because it's after that. But everything that comes before that is also amplified. So this includes the noise of the LNA itself, because most of the times, and it's a valid way to model noise, we model the noise introduced by the LNA as a noise source that is present at the input. So this means that if I increase the gain, I'm actually also increasing some components of the internal noise that I see in a receiver chain. Yeah. There is another point that the noise that is introduced by an LNA as well as the RF noise always usually increase with bandwidth because it's a specific spectral density, which as I have more bandwidth, all the contributions start adding up. But the quantization noise actually doesn't work like that. It's because actually it's not a noise, it's an error, and it's distributed across the entire bandwidth, but I'm not going to get into that in more detail. Okay, and then for external RF noise, well, I have the thermal noise, which I can do absolutely nothing about, and then I have interference. And interference, if it doesn't come from our network, again, we can do very little about this. So, and for the sake of the discussion, we are not going to get into multi-cell deployments. So we will assume that also we have no level of control about the RF interference. Okay, now for the remaining of the talk, you are going to see some graphs with some measurements about noise. And I thought it would be useful, it's a useful moment for me to introduce a hidden little tool that we have in the srsRAN code base. And we call this the RX Power Analyzer. So this is a self-contained application that uses the same drivers that the G0B uses for as far as radio is concerned. And it is useful to characterize the received noise that you see in a USRP. So basically, it has three purposes for us. We can use it to measure the internal noise. And we do this by terminating the antenna port. So you get a USRP, you put an RF termination, you run this program, and at the end what you will have is power measurements for a range of gains of received gain steps. And this is actually the internal noise that is sampled by the device itself. Then, if you connect an antenna to it, and you do the same, you will get measurements of power that is the contribution of the internal noise, which of course we cannot eliminate, plus the external noise, which is coming from the RF environment. And this could be, again, thermal noise, interference, whatever is going on over the air, you will get that. And then this application also allows us to transmit a signal using the USRP at the same time that we do these input power measurements. The signal that we transmit is completely random in nature, and it's just there to serve as an example of a signal that could be coming from a UE, but it's just random data. The idea and the usefulness of this is that it allows you to characterize the receive gain, basically how the actual receive gain of the USRP is affected when you change the RX gain parameter in the G0B. And the reason why this could be important is because, well, you can find out, you will find this out if you do it. It is not a linear curve. And the reason for that is because in a modern receiver, you have actually many places where some internal resistors change that control the total receive gain. So when you move above a specific value, you will see, oh, now this resistor changed, and maybe if I increase the gain by 1 dB, it doesn't result in a 1 dB increase. Maybe it's half dB, maybe it's 2 dB, I don't know. It depends on the transceiver. Yeah, again, this application has some basic parameters. You get the idea that basically you can do a gain sweep and get power measurements out of each of the sweeping points. And then this gets dumped into a file, and then you can process it in MATLAB, in whatever framework you want, and you can display the information. And then here you have like a example one-line command to launch this with some of basic configuration parameters. Again, I think that these slides should be available after the talk, so you will have this. And if you don't, and you have further questions after the talk, we can talk about it. But this is the sort of data that you get if you use it. So in here, we have done this with a USRP. We have done these measurements for a range of received gain from 40 to 75 dBs. The red curve is terminating the receive port, so here you only see the internal noise. Then the blue line is with an antenna. So as you can see, in this particular case, the RF noise is significantly higher than the internal noise. And then the three remaining curves are the gain that the power that we measure when we also transmit a random signal at different transmission gain levels. It's noteworthy to mention that the green curve, as you see towards the top right, is showing saturation. And the reason you see that is because it's approaching 0 dB FS of measured received power, which means that at this point, you are saturating the receiver. Okay, so again, let's go back to our typical, very simplified model of a receiver chain, and let's talk about the design parameters that we have in order to optimize the receive gain and RF power of our system. So basically, we have control over the input RF power because we can set up the P0 nominal, which the input power depends on. And we have control over the receive gain because it's a parameter that we can set up in the G node B. And the relevant characteristics of the receiver chain is the LNA noise figure and the maximum signal level that our analog to digital converter can sample, which we call the full scale input power. So if the signal reaching the analog to digital converter goes above this value, it is saturating and we no longer get past this because we have reached the maximum bit depth of the analog to digital converter. So what does this mean for us? Well, if we increase the Rx gain, we increase the uplink Rx signal power that is reaching the analog to digital converter because the LNA is before that. But we are also amplifying the RF or internal noise contributions that are before the gain control element. So if you have a more complicated receiver chain with multiple gain control points, this translates into, if I increase the gain at this point, all the noise sources before that are also amplified. Then increasing the receive gain also decreases the required P0 spectral density target for reaching the same level of signal at the analog to digital converter input. No? This makes sense because if I decrease the receiver chain total gain, if I increase it, the level of power at the input also can be decreased to reach the same signal level at the output. And this last statement, that it potentially decreases the available Rx dynamic range, is better to see with the previous picture. So I explained before, the red dotted line means saturation. We cannot go above 0 dB full scale. The blue line is the noise floor of our system when we have an antenna attached, which is what we really care about. Of course, our useful signal that we want to try to extract information out of has to move between these two values. And ideally, it should be as furthest away as possible from the noise floor. Now, as you can see, if the receive gain is very low, then this range is good enough. But as we start increasing the receive gain, because we amplify also the noise and the interference, the window that we can place our signal on starts to decrease. And then it means that if there are some errors in the uplink power control, let's say that the path loss estimation that the UE performs has some measurement, some level of error, it's much more likely that it places the power of the signal outside of this window. So this is something that we need to take into account. Then, what does this mean? Well, we need to find a sweet spot for the receive gain. In order to do that, we can analyze these different noise contributions. So as I said, there is the receive power, then the equivalent input noise to the LNA, which is a factor of how noisy the LNA is, and then the quantization noise, which we can also model as an input noise at the input of the ADC. Now, doing this, we can extract an analytical expression for the signal-to-noise ratio, which is a direct measurement of the channel capacity, at the output of the ADC, which is the SNR that we will see in the software, so in this case, in the physical layer. And it is this expression to the right, which includes the received power, of course, and it includes all the noise contributions, the noise coming from outside the system, so thermal noise plus interference, the equivalent input noise of the ADC, so how noisy our receive chain is, and the quantization noise. And it also includes this G of R, which is the receive gain. So as you see, because the receive gain is before the ADC, it has the effect of diminishing the impact of the quantization noise as we increase it. But we could think, okay, then if this is the case, why don't we just keep increasing the receive gain? No, I mean, it looks like it's free to do so, but no, that's not the case. And the reason it's not the case is because we cannot go over the ADC maximum input level. So we need to establish a relationship between the power at the input of the ADC and the received power that we have at our antenna. And a reasonable way of doing that is to say, hey, what I want to do is to have a healthy signal level at the input of the ADC. How do I do that? Well, I want to move as close as possible to the full scale, to the maximum input level of the ADC without going over it. How can we do that? Well, I take into account the maximum output level of the ADC, this POL, and I divide it by the dynamic range of my signal, which is the peak to average power ratio we talked about before. So this would be the best possible input power at the ADC, at the analog to digital converter. And then, if you look at the schematic, you see, okay, I'm at this point. I know what power do I want here. So what power do I need at the antenna to reach it? Well, it's very easy. Assuming this is unitary gain, which is not the case, but for the sake of discussion, let's say it is, then I need to divide by my receive gain. And we come out with this expression. And now, if I combine both of them, I see the real picture. And the real picture is that once I relate these two parameters, once I establish this inversely proportional relationship between the receive gain of my system and the RF power that I expect at the input of the antenna, I see that actually, if I increase the receive gain, because this forces me to have less power at the input, it actually has the effect of making the RF noise and the internal noise contributions that are before the LNA much more prominent in the overall SNR computation. And it makes sense, because I'm actually decreasing the power of the signal because I need to reach a specific level at the ADC. So now what do we do? What do we do with this? Well, we can say, look, if the main contribution is the quantization noise, I don't really care about this part. So I just keep increasing the gain free of cost, because it doesn't really have a big effect. When does it start to be a problem? It starts to be a problem at the point where the contribution of the noises that are before the gain control element are similar in magnitude to the quantization noise. At this point, I have to take them into account because they are going to affect the system. Yeah, so that's the problem we face. And why do we use this? Well, we can use this to determine the maximum receive gain that we can use without having an increase, a significant increase in the overall noise of the signal that reaches the digital side of the G node B. Okay, so we have a way to set up the maximum desirable receive gain. Now, what about setting up the minimum desirable receive gain? Well, in this case, it makes sense to say, look, then if the only thing we care about is noise and SNR, let's just put a receive gain of 0. No, and then that's fine, because then there is going to be very little noise. Of course, the UE transmits a lot of power, so it's going to overcome all the interference, and it's fine, and we don't really care about anything else, so it should work really well, right? Well, yeah, but if you do that, and then you move the UE 10 meters away, suddenly you don't have a signal anymore, because the UE is going to reach its maximum transmission power very quickly. And what this means is that your cell range will be greatly reduced. So, as part of our cell planning, or our initial planning when we decide how to set the system up, we need to consider, hey, I probably cannot expect the power at the input to go above a specific level, because the UE is going to have a lot of issues trying to reach this power level. As soon as I move it out of the space, it's not going to be able to do so, and then the system doesn't work. This results in a maximum level of RF power that I can expect of the system. And because there is an inverse relationship between the RF power and the receive gain, this results in a minimum receive gain that I should use in the configuration. And between them, we have a sweet spot. How does this look in our measurements? So this graph has been obtained, again, by using the RX power analyzer that I showcased before. In this case, it's a different USRP, but what we see is very similar. So the blue line is the power measurements when we terminate the receive port. So this is only internal noise. And the red line is measurements with an antenna. In this case, they look much more similar, no? Well, this is band 79. So of course, in band 79, there are no commercial G0Bs, at least in the place where we did these measurements. And what this means is that the interference is way less prominent. So it looks like, in this case, the internal noise contributions are much more prominent, which is good for what I'm going to explain now. So if the array receive gain is very low, what we see is that in this situation, the predominant noise source is the quantization noise, which means that if I increase the receive gain, the noise floor doesn't increase. This means that we can keep increasing free of any penalty. Now, on the opposite side of the graph, on the right side, we have the opposite picture. At this point, we have increased the receive gain to a point where it's actually amplifying greatly all the noise that is before the low noise amplifier. And what this means is that at this point, yes, I can amplify the signal, but I'm also adding a lot more noise, so it's almost pointless to keep increasing the receive gain. And you will see this with a USRP. It gets to a point where you just keep increasing it and nothing really changes, no? So what is the interesting sweet spot? Well, it's this part over here. It's the change of tendency. At this point, it means that all the noise contributions are similar in magnitude, so it provides us a sweet spot, which is the sweet spot we had here before. So, as a summary, RX gain should be high enough that the UEs don't run out of power headroom as they move away. It should be high enough that the analog to digital converter quantization noise is not the limiting factor for performance. But it should also be low enough that the uplink receive signal doesn't saturate my receiver, in this case, my analog to digital converter. And it should also be low enough that the RF plus LNA noise does not reduce a lot the available dynamic range. In some situations, it's impossible to meet all of these criteria. And then, of course, as everything in life, we have to decide what we really care about. If you care about range, increase the dynamic range. You know that you will be adding more noise, but the UE is going to have less trouble reaching your P0 nominal target. If you care about maximum possible channel capacity, decrease the gain, and, well, you have to pay the price of less range. Yeah. Yeah, okay, great. So yeah, hopefully this answers these questions about the power calibration procedure. So we set the P0 nominal to reach a specific target for receive power. Then we adjust the receive gain to move between this compromise. And I have excluded some considerations from the analysis, which are not, I didn't really talk about them. And in here, well, we have some experimental findings with a very simple setup, with a V200, an external power amplifier. And what we found out is that using, well, this setup, we don't have isolation between the transmit and receive chain. And because this is a TDD G0B, which we deployed, the downlink signal is having a huge effect on the uplink performance. So as I said at the end, the conclusion is that, well, if you don't have an external power amplifier and you use this system, well, it works, the uplink looks healthy. But the moment you add an external power amplifier, it's not enough. You cannot just say, hey, I put an external power amplifier, now I have more downlink power, everything looks fine. No, you will screw up the uplink. And what this means is that you need to have a proper RF front end if you want to achieve decent performance and decent range with a USRP. Otherwise, it's totally impossible to find this sweet spot. Okay, thank you very much. If you have further questions, I can address them at some point. So thank you.